Okay, so let's continue. So in the second part of the talk, I would like to cover some of the more recent works, and just to remind you briefly, we've seen the geometric deep learning blueprint that allows us to derive from first principles some of the architectures such as CNNs, GNNs, and transformers, and so on. And essentially, we distinguish between the domain with its symmetry group, the signals on this domain, and the functions that act on these signals. And in particular, we're interested in functions that are equivariant or invariant with respect to the group action. And graph neural networks are a particular instance of this blueprint where the domain is the graph, the symmetry is the permutation group, reflecting the fact that we don't have a canonical ordering of the nodes. Then the representation of the group is a permutation matrix that acts on the signal that is defined on the nodes, the Fisher vectors of the nodes, and then message passing implements a permutation equivariant function. So we've seen different instances of this blueprint on different domains, whether it's grids, meshes, and graphs, but somehow there is a continuous counterpart to the first two objects, right? So grids can be considered as a discretization of the plane, or maybe more generally of some homogeneous space, and meshes can be considered as a discretization of a manifold of a two-dimensional surface. We don't have an immediate continuous model for graphs. To me, this is personally very disturbing. So we want to think of something that would at least in some sense be a continued analogy of graphs as well. Now, graph neural networks again implement this geometric deep learning blueprint. So they work locally by aggregating the set of neighbor fishes in an invariant way, and then apply this aggregation at every node. So we get a permutation equivariant node-wise function. And we've seen that this kind of architecture, if we choose wisely an injective aggregator, is equivalent to the Weisfeld-Lehmann graph isomorphism test. Now, we've seen this example of non-isomorphic graphs that are WL equivalent because it's a necessary but insufficient condition, and it's interesting to see why this happens. So, from the perspective of the Weisfeld-Lehmann algorithm, what it sees is that every node is this kind of a rooted tree structure. And these two nodes in these different non-isomorphic graphs will see exactly the same structure. So it will be colored in the same way. And this is why these nodes are indistinguishable. Now, Chris will talk about more expressive topological message passing, where we can actually enrich the graph with some extra structure. In this case, we can talk about, for example, about cellular complex. So we say that it's not just a collection of nodes and edges, but there is also a face here, or a cell that they represent by different field colors. And we can do message passing not only between nodes and edges, but also between these higher order structures. And this gives more powerful architectures. There is also the KWL equivalent graph neural networks that were covered in the previous lecture, which at the expense of more computational complexity allow to be more expressive. However, the most common way of increasing the expressive power of graph neural networks is through positional encoding. So positional encoding is a kind of pre-coloring of the nodes of the graph. And if it is, for example, structure aware, I can distinguish between different graphs in this example, right? Because, for example, if I can count the number of triangles a node participates in, it will be 1 in this graph, and it will be 0 in this graph. And again, there are multiple ways of doing positional encoding. Even random node fishes are maybe an extreme example. You can use Laplacian eigenvectors, and bags of subgraphs is another recent kind of work that can be thought of as a form of positional encoding, and Fabri will cover it in his talk. But bottom line, we have no idea how to do positional encoding in a principled way. Well, maybe there are some views on it, right? So you can think of it as a learnable process, but I would like to present a geometric perspective. And final thought is the phenomenon of oversquashing and bottlenecks. So this is an interesting phenomenon that is a little bit controversial. So there was always some kind of difficulty to design deep graph neural networks. I even wrote a somewhat controversial post about it that attracted some criticism about do we need deep graph neural networks, and it discusses a paper that was published last year about bottlenecks in graph neural networks, showing that if you have this unlucky combination between a problem that depends on long-range information, so I need to get information from nodes that are not immediately in my neighbors, but maybe a few hops removed. If I have many such neighbors, so the volume on the graph grows very fast, like the situation in small world networks such as social networks, I get this phenomenon of over-squashing, that I have a lot of information that I need to squeeze into a single vector. And it appears that there is some characteristic of related to the connectivity of the graph that contributes to this over-squashing. So this was named the bottleneck. And empirically, it was shown that by doing the graph rewiring, basically by decoupling the input graph from the propagation mechanism, this phenomenon can be alleviated. And there are multiple ways of doing graph rewiring, for example, by sampling the neighborhood, using multi-hop filters, even using the complete graph. So this was suggested in the bottleneck paper by Uri Alon. Diffusing the connectivity, the famous architecture DIGL, the diffusion improves graph learning from the group of Stefan Günnemann in Munich. You can also make the graph learnable like we did in the dynamic graph GNNs, but again, the bottom line, we have no idea how to correctly rewire the graph. So, or at least not a principled approach. So I would like to discuss this as well. So these are 3 different papers that we did at Twitter with co-authors. Basically, neural diffusion. So 2 different models of neural diffusion PDEs, grand and blend. So that was respectively our ICML and URIPS paper. A more recent collaboration with Oxford on graph rewiring through curvature. Basically arguing in favor of something similar to backward Ricci flow. And again, we have blog posts on all these papers. So if you want a brief and higher level introduction, that this will be probably a good starting point. So let me start with diffusion. So diffusion has a very long history, and probably the first attempt to study it rigorously in the setting of heat diffusion was an anonymous publication in the Transactions of the Royal Society, published in 1701, that was written in Latin about the scale of heat. And even though it was published anonymously, everybody somehow knew that it was written by Isaac Newton. He would become Sir Isaac 4 years after. And they described what nowadays is called the Newton's law of cooling, which states in modern terminology that the temperature a hot body loses in a given time is proportional to the temperature difference between the object and the environment. So I should say that Newton at that time used what could be considered a hodgepodge of terminology. He used the Latin word calor, which means heat. And in modern physics, it has the meaning of the flow of thermal energy measured in joules or in calories. And instead, we should use the more appropriate term temperature, the average kinetic energy of molecules, that is plus the units of degrees Kelvin, which has not yet been invented. So it took another century for the diffusion to be understood properly, using differential calculus that already existed, and Newton was one of those who invented it. So this was due to Fourier. And what's now is called the Fourier heat conduction law, that states that heat flux resulting from thermal conduction is proportional to the magnitude of the temperature gradient and opposite to it in a sign. So unlike Newton's law of cooling, which is global, this is a local rule. And finally, the last bit is some form of conservation law that was derived by Adolf Fick. He actually started his career as a prosector. Basically, he was dissecting dead bodies in Zurich, and he studied chemical diffusion and came up with what is called the second law of diffusion of Fick, stating that temperature change in time equals to the heat flux through volume. So it's a conservation law. So put together, we can now write the diffusion equation. So here we have some stuff, right? Let's think of temperature in some medium. The difference in the temperature creates the heat flux, right? That is proportional to the negative gradient of the temperature. Fixed law provides us the conservation condition, that no heat is created or disappears. So all the temporal derivative here is attributed to the divergence of the flux. And together, this gives us the heat equation. So the left-hand side has the temporal change of temperature, or any quantity that is diffusing, and the right-hand side tells us how it diffuses in space. So it's spatial derivative, divergence of a gradient multiplied by some function. And if this function is constant everywhere, we're talking about homogeneous and isotropic diffusion. So the stuff propagates in the same way at every point in every direction. And we can interpret this diffusion equation as the gradient flow or the minimization of what is called the Dirichlet energy. Or in the Euclidean case, we actually can give it a closed form solution. It's convolution with the Gaussian filter. So it smoothes out, it's a low-pass filter, and the variance of the filter increases with time. So at infinite time, everything will be constant. We can also look at non-homogeneous diffusion, where the diffusivity is position dependent, and in particular can depend on the signal itself, or the most general case of anisotropy diffusion, where it's not only position dependent, but it's also direction dependent. So now we have a matrix function that is called the diffusivity tensor. So this non-homogeneous diffusion that was erroneously named by Perron and Malik anisotropic diffusion, in fact it is isotropic but non-homogeneous, attracted a great deal of attention in image processing, and due to the idea that, which is very smart and I think very beautiful, is you can define filtering, because diffusion, as we've seen from this expression of convolution with the Gaussian filter, it's a low-pass filter, so it can do denoising by averaging pixels around and averaging out the noise. But it's smart filtering that it doesn't diffuse across edges. So it preserves discontinuities in an image. And the reason why this is important, if you look at this image on the left that has noise, if you diffuse it homogeneously, we destroy the visually important discontinuities, which for our visual perception are crucial, whereas non-homogeneous diffusion, the Perron and Malik diffusion, preserves these discontinuities and still averages out the noise in piecewise smooth parts. And there are many follow-up works on this topic. An entire field of PD and variational image processing was born in the 90s and the 2000s to be wiped out later by deep learning, but there are entire books on this topic. So what we'll try to do, we'll try to reproduce the same thing for for graphs. Basically, on graphs, we can define a complete formal analogy of all the operators that I described in continuous case. So we have the gradient, which is defined just as the difference between the features at node I and node j. We have the divergence that takes the now the edge features in the edges that emanate from a node and sums them up, maybe with some weights. And same way as in the continuous case, these operators are adjoint. So if I take the appropriate inner products, I can move things around. And we can define the Laplacian, which is the divergence of the gradient, and geometrically can be interpreted as the difference between myself and my neighborhood. So if I massage this formula, you can easily see it. So the diffusion equation on graphs looks exactly like the continuous one. So we have, again, the formal analogy of the same structure. So this is the gradient, this is the diffusivity, this is the divergence. We assume that the diffusivity is normalized to 1, just to make things easier. And this is the temporal derivative. So the time here is continuous. And this is a nonlinear differential equation. It has to be solved numerically, and the way to do it is to discretize the time. So we discretize it here with constant time step tau, and we replace the continuous derivatives with forward differences. So this gives what is called the forward Euler or explicit numerical scheme for solving this diffusion equation, and I can write it in matrix vector form like this, or shorter version. So this is the iteration formula. So the next step in time, k plus first step, is obtained as the previous step, transformed by some matrix that depends non-linearly on the features, right? So it is a linear transformation, but basically it's a matrix-valued function that depends non-linearly on x. So the matrix, importantly, has the same structure as the graph adjacency matrix. So it is local and sparse. And this scheme is stable for sufficiently small time step, in particular between 0 and 1. So in practice, it means that you will need to take small time steps for this scheme to be stable. What you can also see that for time step tau equals to 1, we get the graph attention network. So you can interpret the diffusivity as the attention function. And what we'll be trying to do, I can already anticipate, we'll make this function parametric and we'll be learning it. Okay, so now, of course, this is maybe just one way of discretizing differential equations. A different way would be to use semi-implicit or backward discretization, in which case we use backward time difference. And again, you can write it as a matrix vector form. And it is similar, but now you see that the matrix appears on the left-hand side. That's why this scheme is called implicit, that in order to obtain the next iterate, we need to solve a linear system of equations, or approximately invert the matrix P, which means that the inverse now is not necessarily sparse. It usually will be a dense matrix. So we can interpret it as a kind of multi-hop filter. If previously our iteration matrix had the same structure of the adjacency matrix, now it affects multiple nodes of the graph. And the advantage, of course, that we have here is that semi-implicit schemes are unconditionally stable. So we can make tau as big as we want. Typically, the trade-off will be the accuracy, but again, here we don't care about the accuracy because we are learning this diffusivity to solve some downstream task. So basically, we are interested in solutions of differential equation that we can obtain by parameterizing different diffusivity applied to different input. So here are just some examples of different numerical schemes that exist in the numerical analysis literature. And what we've seen are just these two extreme examples. There are multi-step, adaptive step size schemes such as Runge-Kutta and many other solvers. So this is what we do with this architecture. So we call this graph neural diffusion, or GRAND, admittedly very modest acronym. So we start with some input features. We use them as an initial condition. We solve the diffusion equation for some time t, applying the diffusion equation with learnable parameters. And here what is important, we assume, and this is by choice, that the diffusivity is not time dependent. So in the language of graph neural networks, it means that the parameters are shared across layers. We don't have different attention parameters in different layers. So here layers correspond to different iterations of the solver. And what we gain is, of course, a new perspective on old problems. So as we'll see, we'll be able to address things like depth over smoothing bottlenecks. We also gain new architectures. So first of all, existing architectures can be formalized as different discretizations of the graph diffusion equation, but many other more efficient solvers such as adaptive, implicit, multi-grid, multi-step solvers do not have immediate analogies in the graph neural network zoo. And there will probably be new architectures that will arise from this analogy. There are some theoretical guarantees about stability convergence that come free of charge if we basically we can leverage the theory of discrete partial differential equations. And it also offers deeper links to other fields that are less known in graph neural networks, such as what I will show, differential geometry, and more recently in some works that we're currently doing, also algebraic topology. So the question of depth that I mentioned in the beginning, right, that it's difficult to train deep neural networks. By depth here, we don't have any more depth in the standard sense of the number of layers. By depth here, we mean the diffusion time. And if we use simple explicit schemes where the step size is fixed, then we can have the relation between the number of layers as the diffusion time over the step size. But in general, in adaptive schemes, we can have bigger steps when necessary, so we use less layers. And in implicit schemes, we can trade off between depth and width, right? So the size of the filter and how many times we apply this filter. And here you can see an example of the depth, right, or the number of diffusion steps and the accuracy on different benchmarks. And you can see that we don't lose accuracy with depth. And of course, in performance, nowadays you cannot publish a paper without obtaining state-of-the-art results on some standard benchmarks, so take it with a grain of salt. What is important, though, to see that if you compare, let's say, to GATT, which performs more or less on par, maybe slightly worse on some data sets, we have about 20 times less parameters. That's exactly because of this time-independent diffusivity, in other words, shared attention parameters across layers. Now, what we've seen here was a way of a continuous analogy of time. Right, so the diffusion was still a discrete equation in space, and this is not yet satisfactory because we wanted a continuous model for graphs, right? And if we again take a step back and think of diffusion, let's say in the plane, so in the plane we have many different ways of discretizing our derivatives, right? So if I discretize the plane as a grid, I can take different numerical schemes for the Laplacian, let's say. So I can discretize it with these four neighbors, or with these four neighbors, or with these four neighbors. And because the operator is linear, any linear combination will work. Okay. So basically, any linear combination of these discretization works. So we want something like this for our graphs as well. So we want a continuous analogy. And here is the second part of geometric flows that I mentioned. So basically, we want to look at this problem slightly differently. Just a second, please. I see that my camera is not is a little bit blurred. So basically, what we've seen in the Perron and Malik model is a nonlinear diffusion equation, right? That had this adaptive diffusivity function that told the diffusion when to stop, where to diffuse faster, where to diffuse slower. A different way would be to think of it as a linear but non-Euclidean diffusion. So we think of our image as a surface or a manifold in higher dimensional space, and basically we run the diffusion on this manifold. So the filter now somehow lives on the surface. And more formally, we consider the image as embedded in this joint space where we have the feature coordinates and the positional coordinates. So if you think of an RGB image, then it will be a two-dimensional manifold in a five-dimensional space, right? So we have the positional coordinates, the position of the pixel, so it's 2 dimensions, plus the feature coordinates will be R, G, and B, 3 color channels, 3 extra dimensions, okay? So on this manifold, we can define a pullback matrix. So the structure of the space in which the manifold is embedded defines some canonical Riemannian metric on the manifold. I can describe it in this way. And we can write a non-Euclidean diffusion equation that is called the Beltrami flow. So it's the gradient flow minimizing what is called the Polякov energy. So it's the non-Euclidean extension of the Dirichlet energy, or it's called harmonic energy in differential geometry. Or Polякov action or Polякov functional in high energy physics, and in particular in string theory, where it gives rise to some exotic models of particles. So the Beltrami flow is named after Eugenio Beltrami, one of the early Italian differential geometrists. That actually, one of his achievements was proving that Lobachevsky geometry is self-consistent. So that was the first time that it was understood that non-Euclidean geometry is real. So you can see here that basically by choosing this metric, we can recover the anisotropic diffusion that we've seen before. So Perron and Malik can be obtained as a special case of the Beltrami flow. And again, the space into which we embed doesn't need to be Euclidean space, so it can be a manifold as well. So there is really a richness of structure that can be used here. So as before, as in Grand, we do exactly the same thing. So we can write an analogy of the Beltrami flow for graphs. So in this case, each node is equipped not only with feature coordinates, but also with positional coordinates. So I tried to my poor abilities to draw it here. So we have the positional space. So the nodes of the graph is represented geometrically in some space. So it's embedded in this space. And these are the feature coordinates. And when we apply diffusion to both, basically the evolution of the x component is the standard feature diffusion. The evolution of the z component, you can think of it as a kind of graph rewiring. So if we could represent the graph in the positional space, I actually don't need a graph. I now can think of it as just a convenience, right? So I can think of nearest neighbor graph in the positional encoding space. And because this is something that we optimize for the downstream task, this is learnable. So the diffusion produces the optimal positional encoding that is good for the specific task. So there is some subtle difficulty, well, if you're familiar with, better with differential geometry, so there is no immediate analogy of metric pullback on graphs. So the analogy is not complete. I think now we have a better picture, but it didn't get into the paper. But allow me to skip it for the sake of brevity. Probably I would like to show you this picture, which explains much better when I tried to explain in the previous slide. So this is graphics created by James Rowbotham, one of the lead authors of this paper. So you can see the core graph where the nodes are represented by these colored circles. The colors represent the features, some low-dimensional projection, and the positional encoding is represented by the coordinates of the nodes. And you can see that it's both the features and the positions are evolving, and the graph is rewired. You see that the graph is changing as we diffuse. So we call this architecture blend, and you can see that many previous architectures can be considered as special cases. So again, you can think of it as a discretization of this non-Euclidean diffusion equation, and it also works nicely in practical applications. So let me move to the last part, and I'm slightly over time, so let's now discuss bottlenecks and how it relates to the notion of curvature in differential geometry. So in this last picture, we've seen something that is a little bit disturbing, maybe from the perspective of machine learning, that somehow we have diffusion on a domain that is moving under our own feet, right? So the graph is evolving. And in differential geometry, this is a very standard thing to do. So applying some evolution equations to the domain itself, to the manifold, is very common. And one particular way of doing it is what is called the Ricci flow. And it's an equation that evolves the metric of the manifold itself. And structure, it's a little bit similar to the diffusion equation. So you see the temporal derivative of the Riemannian metric on the left-hand side. On the right-hand side, you have what is called the Ricci curvature, which is a second-order derivative. So that's why structure, sometimes it's referred to as the diffusion of the metric, even though the properties of this evolution are pretty different. And what it does, basically, it takes a manifold and changes its shape, and the diffusion is faster where the curvature is stronger, and slower where the curvature is smaller. And the Ricci flow was pioneered by Richard Hamilton as a tool to try to prove the famous Poincare conjecture. So Poincare conjecture allows to describe topological spheres by basically the way that they collapse, right? So you can define a two-dimensional sphere by the fact that you can take any closed curve and collapse it to the point. So Poincare conjecture that this is also true in 3D. So for some reason, it is easy in 2D, it is easier in 4D, but 3D turned to be a difficult case, and it was finally proven by Grigori Perelman about 20 years ago. That was the breakthrough of the year in 2006, according to Science. And he exactly used this mechanism of Ricci flow, well, slightly more complicated version of Ricci flow with surgery, to prove the Poincare conjecture. Now, what does it have to do with bottlenecks? So we've seen that this phenomenon of overscorching, which is failure of message passing to efficiently propagate information in the graph, is caused by some structural characteristic of the graph that is referred to as bottleneck. Usually these two things are conflated, but we shouldn't. Bottleneck is distinct from oversquashing. So oversquashing is more acute in problems with long-range dependencies that require information from many neighbors away, like in chemical problems where we have a molecule and maybe some properties depend on two atoms at two ends of the molecule. It occurs in graphs with exponential volume growth, where we have too many neighbors, so to say, and it tends to deteriorate with depth. And we also know that it is alleviated by graph rewiring, and what we try to do is to formally define oversquashing related to geometric properties of the graph, in particular negative curvature, defined in some sense, and then do some form of rewiring that is surgical and resembles or inspired by the Ricci flow. So it's an evolution of the graph by its curvature. Okay? So let me briefly run through this, and I will skip some technical details. So first of all, if we consider a message passing neural network of this form, so we assume that we have boundary gradients. Basically, what we try to do is to describe oversquashing as some kind of low sensitivity. What do I mean by this? Is that if I look at the output of some layer of graph neural network at node I, and how it depends on the input at some node S, right? Here that is R hops away, right, or R geodesically distant. I can write the Jacobian of this representation and see basically how small it is, right? So if this gradient is small, if this Jacobian is small, it means that I am not sensitive on the input, right? It means that this information doesn't propagate well. And I can write this bound, and you see that the structure of the graph comes into the play here, but not in a very understandable way, right? So it comes into this bound as some power of the adjacency matrix, so it's not clear where the bottleneck is, right? You can see that some pathological examples, like trees, for example, are the worst case in the sense of the bottleneck, right? So what we need to try to describe is something more nuanced, something local that tells us what happens in graphs. And intuitively, we expect that, for example, a tree will be very different from a grid, right? So on a tree, we have very strong oversquashing, as shown in this example. On the grid, we don't, right? So in geometry, the standard way of distinguishing between these objects is curvature. And in particular, Ricci curvature can be described in the following way, that we take nearby points on our surface. We send two geodesics that are parallel, right? So they're in the same direction and at the same speed, and we can check whether they will converge. And in this case, we have a situation that looks like the sphere. They remain parallel. In this case, we are flat or zero curvature. So this is the Euclidean space, or they diverge. So this is the hyperbolic geometry or Lobachevsky geometry. So we can think of the same construction on the graph. So on the graph, we have nearby points in the sense that they are connected by an edge. And if I send geodesics, right, or if I shoot edges from these points, if they tend to form triangles, I have something that looks like positive curvature. So this will look like a clique. If they remain parallel, right, it means that they will not converge. They will form rectangles. And if they form nothing, right, so if they become more distant, then I have a tree. So basically, we need some notion of local combinatorial curvature that will be consistent with this kind of intuition. And this is the definition that we have here. So it doesn't really matter. Basically, what we count here is the number of these triangles and rectangles in the graph. So there are several notions of curvature on graphs. One of them is the Foreman curvature. Another one is the Olivier curvature. So we call this the balanced Foreman curvature. So it's similar to Foreman, but it is modified to be consistent with our previous examples. So for cliques, we have positive curvature. For grid, we have zero curvature. And for trees, we have negative curvature. Okay, so that's what is important about it. And we can also show that it's a lower bound on Olivier curvature that theoretically is the most studied. It's related to parallel transport. and it was studied by Fields laureates Cedric Villani and Pigali. And we can also show that if we have a positively curved graph, where basically every edge has a positive curvature, then the volume growth is polynomial. We don't have this kind of too many neighbors. And we can also find it bound on the Chigger constant, or the spectral gap of the graph. So this is a spectral characteristic telling how clustered the graph is, how strong communities it has. And the main result of our paper is this theorem that, again, might sound a little bit bombastic and complicated, but what we show here is that if the graph has a negative curvature, then there exists nodes that are responsible for oversquashing. So basically we can upper bound this Jacobian, right? And it means that oversquashing is caused by negatively curved edges. So the negative curvature is the one to blame for this phenomenon. And the procedure that we propose for dealing with it is what we call stochastic discrete Ricci flow. So it is similar to backward Ricci flow. Basically what we do is we pick up the most negatively curved edges and we try to remove them to improve the curvature of the graph. And optionally, we can also add new edges in the graph to compensate for the edges that we take out. And this offers a graph rewiring procedure that acts very differently from, let's say, DIGL, the diffusion improved graph learning paper of Stefan Günnemann, that is using diffusion to change the connectivity. And in particular, they propose personalized page rank based rewiring, where you embed the graph into using the personalized page rank for every node, and then you rewire based on this embedding. And you can think of a new adjacency that is obtained by this formula from the original adjacency. What we can show that for a given sigma, which is the diffusion strength, the Chigger constant of the graph that is rewired by DIGL is basically is upper bounded by this quantity. So it is controlled by the original Chigger constant of the original graph. So if the graph to start with was bad, it will not be improved, right? I cannot really improve it. And here's an example. So an example of two clicks connected by a bridge. So this is a graph with a very small Chigger constant. It's nearly zero, right? And in the limit, when n goes to infinity, it will be close to zero. So no matter how we try, the Chigger constant of the rewired graph will be close to zero. It will be dominated. It will be controlled by the Chigger constant of the original graph. And basically, the conclusion is that diffusion of connectivity doesn't necessarily improve graph bottlenecks. So I think the name DIGL, diffusion improves graph learning, was a little bit too optimistic. And we can also think of it, we can interpret it in the way that random walks tends to connect nodes with small diffusion distance, so basically inter-community. And it is expected to work well in homophilic cases, where the node features or the node labels are aligned with the graph structures. So homophily means that my neighbors are similar to me. And also the downside that the result of topology change can be very significant from diffusion. So if you compare it to the curvature-based rewiring, DIGL has limited effect on bottlenecks, at least in some situations. The stochastic discrete Ricci flow can reduce bottleneck arbitrarily. The DIGL tends to change graph topology significantly. In the case of Ricci flow, it is surgical in nature, so it doesn't change the topology significantly. DIGL tends to connect nodes at small diffusion distance, so basically to optimize inter-community. And curvature-based approach can connect nodes across communities, so basically reach out to other communities. And as a result, it is good in both homophilic and heterophilic cases. So this is an example of a homophilic graph, where basically there is strong connectivity between similar nodes, right, with similar features. And in this case, the diffusion-based rewiring does only good, right? So it reinforces, right? So I add more neighbors that look more like me in the same community. Basically, the structure of the graph is aligned with the structure of the features. And as a result, I have more features to average in my diffusion process, my graph neural network, so the results tend to be better. In case of curvature-based rewiring, I will be doing just a few touches, so it will be surgical, so it will not destroy the communities. But when the graph is heterophilic, diffusion rewiring creates disasters. And here's an example of a graph. So this is a Cornell graph, which has actually low homophily. Well, I don't show the features here themselves. I show the node colors represent the Jacobian, basically our criterion of overscorching, and the edge color represents the curvature. So this is how Deagle rewires. You see that the graph is completely different. So we added 300% new edges. Curvature-based rewiring is much more subtle, and you see that it improves the Jacobian. So if the color becomes warmer, it means that the Jacobian is bigger. It means that the overscorching is less significant. And here are some results. So as expected, in the case of low homophily, Deagle performs worse, and curvature-based rewiring performs better. So it's not necessarily a practical algorithm. I think it's more a viewpoint, an approach to interpret these phenomena of bottleneck from a geometric perspective. And I think it's highlight this interesting, deep and intimate link between graph neural networks, differential geometry, partial differential equations, algebraic topology that I didn't mention, but I think Chris will be talking about it in his next talk. It's a new set of powerful tools to study GraphML problems from different perspectives. It allows to offer a principal take on positional encoding and on graph rewiring. And I think it's just the beginning. It opens many interesting questions and many follow-up work that I expect to see from here. And maybe I will conclude with just one question. Are we done with message passing? So this is what somehow we conjectured. So I wrote this blog post last year about predictions for 2021, interviewing different people. And one of the statements that we wrote was that basically we need to go beyond message passing that dominated 2020 due to the realization of its limited expressive power. I'm not sure that this prediction has materialized, or at least not in the way that I expected. I think we are still within the remits of message passing. We just do it differently and make graph neural networks more interesting, more expressive, more powerful, more efficient. So I think message passing is still not out. I think it still has many things to offer. And this geometric connection is an interesting way of looking at it. So I'm really sorry that I over-abused your patience and my time. So I will stop here, and thank you very much.
Thank you very much, Professor Michael, for this wonderful presentation, and in the second half presenting different perspectives, which helps us understand this from a very interesting domains from which future extension can be drawn. And for example, for positional encodings and wirings, there's still like different new techniques that would be developed. I myself personally will be looking out to follow up from some of these perspectives.
Hi, this is Bishesh. Hi, Michael. Thanks a lot. I'm from the hall, so I'm in the hall with quite a lot of participants. Maybe we can take one or two questions, and but not much perhaps, and then people could discuss more on Discord. First of all, thanks a lot, Michael. It's always insightful, and we couldn't have you here this year, but hopefully next time soon. So anyone with the question? So we'll take only two questions because I think we need to have a break, and then there's other two lectures remaining. So two questions. Who want to be the luckiest ones to ask questions? Okay.
Hello, my name is Suman Sakpada. I wanted to ask the question about the Beltrami flow. You saw that the movement of nodes happened and the connections of the edges changed, right? So are the connection nearest neighbors, or does it depend on some underlying data or something?
Yeah, so if I understand the question, so first of all, rewiring is not necessarily, doesn't need to be necessarily done, right? So basically, if you remember the expression, so the diffusivity function or the attention depends on both positional and feature component. So it is analogous to the way that positional encoding is used in graph neural network architectures. So if, let's say, you use a GAT type architecture, so you just provide this extra information. So basically, the attention will depend on roughly how the features are similar to each other in two different nodes, but also how distant they are from each other, right? Or how their positional encoding is different. Now, if we see that, for example, two nodes become distant in this, in the sense of some metric in this space, that doesn't actually have to be Euclidean. We also show results with hyperbolic embeddings. Then it makes no sense at all to create an edge there. So you can just cut it out, right? If it doesn't contribute much to the attention. So that's exactly what graph rewiring tries to do. So we remove some irrelevant edges and maybe we add edges to nodes that at some point of the diffusion become closer and therefore contain more information. So I hope that this answered your question.
Yes, he says yes. One more question. Do we have a question in the Zoom chat or Discord? I don't know which place we're using.
We don't have any question on the chat so far.
Okay, so one question. Anyone? Think? Yes. Okay, so we've got one question.
Hello. So my question was more regarding the unification. That I get the general gist of bringing existing networks all together, but beyond that, also, is it really about seeing the data in one particular form of bringing the symmetry and invariance on the data sides, or it's all more about the network, the functions, or both together? And is it really from the unification point of view, or actually it's offering us something new, how things need to be designed? I understand that from the unification point of view, whatever exists there, they require some kind of abstract framework that basically allow us to communicate and share knowledge from different domains. That's what it's offering in one regard. But my question is more in the sense of, like, is this particular framework essentially bringing the knowledge together, or actually offering us some new tools to really to know that how networks or the biases need to be injected for this particular data or this particular network architectures?
Yeah, no, it's a very good question. So well, it's always a doubt that when you hear about unification is whether it's something in name only, or does it offer anything new? And I think it does. So I will give you one example. So we talked about graph neural networks, right? So there, the symmetry structure of the domain itself is permutation. So you get this message passing that is permutation equivariant and correctly accounts for the symmetry of the graph. Now, you can also have symmetry of the data itself. And the good example are molecular graphs. So in molecules, the nodes are atoms, and atoms have different kinds of data that should be treated differently. So it can be, for example, the atomic number, which is a categorical feature, and it can be the atomic coordinates, which are geometric features, right? So when you try to predict, for example, the property of a molecule, you want to make sure that you're not sensitive to the orientation of the molecule in space, right? So you want to be equivariant with respect to Euclidean transformations, right? Rotations and maybe not reflections, but at least rotor translations. Right, so your message passing is what is called the external symmetry, using the language of physics. So the symmetry of the domain, or the symmetry of space, whereas basically this rotor translation symmetry of the data is what is called in physics internal symmetry, or the symmetry of the field. And this has been remarkably successful in this field of computational chemistry. I mentioned AlphaFold, where equivariant message passing, right, or they call it point invariant attention, or equivariant transformer, has been used. Another competing architecture from the group of David Baker, a group of protein design, Rosetta Fold, uses SA3 equivariant graph neural networks. There are many more papers that try to do equivariant message passing. So this is a new kind of architectures that have emerged in the past year or two from this blueprint, and they have not existed before. So I think this was only possible by understanding these basic fundamental principles. There are more examples, but I think this is the most prominent one.
Okay, thank you. I think that was a fitting question, trying to get back talk about this generalizing or unifying principle that Michael wanted to share with all of you. That's what I think we're sorry, but we have to limit the questions here, but I think they can ask questions in Discord, perhaps at least today, I hope. And from this side, let's give a big round of applause again. I don't know if you can hear.
Thank you.
Thank you very much. And over to you, Vijay, if you want to wrap up this session.